Welcome to the water cannon lab. Today we're going to be doing an experiment in which we gather force and pressure data from a water cannon, and then we're going to try to recreate that data using an analytical model. But before we start, I'm going to go through a quick explanation and re-derivation of Reynolds Transport Theorem and talk about momentum balance. So Reynolds Transport Theorem is a way of relating a control mass system and a control volume system. It's nothing more than an accounting term, than production accounting. But it's important to understand the conceptual stuff behind the math that we see in momentum balance. So we want to be able to use equations such as production of mass is 0, production of energy is 0, and we need to be able to do that in a control mass system. So what Reynolds Transport Theorem does is it relates for a property n, the rate of change of that property in a control mass with the rate of change of property in a control volume. In order to make this relationship hold, we need to add some other terms over here. So let's go through a quick derivation of how we come up with these terms. Let's assume at some time t equals 0 we have a control mass, and we'll overlay our control volume on top of this control mass such that they're coincident at time t equals 0. So I'll call this Cm at t equals 0 and Cv at t equals 0. Now we'll have a general case here. We're going to allow our control mass to move and deform in space. We're looking at a 2D image here, but think of it as it could be 3D. So we'll allow our control mass to move. Let's say it moves arbitrarily up and to the right to this position. This will be our control mass at some time t equals dt. And then we'll also allow our control volume to move arbitrarily. And we're going to say it moves down to the left. And we know in this control mass that the mass is conserved. So we'll use property n as our property we're going to be accounting. And if you think of n being something simple like mass, you know that n is going to be dn dt for this control mass must be equal to 0 because mass is conserved. So we want to be able to understand what's happening via the control volume because we're engineers and we care about a region in space. Maybe we can measure flows in and out of that region, or maybe measure what's in there at any given time. So we're going to try to relate the control volume to our control mass. Let's think about this in terms of volumes of stuff. And since this is a 2D problem, we're going to do this in terms of areas. So I'm going to label these areas certain letters: A, B, C, D, E, F, and G. And we're just going to go ahead and explain. We're going to express these two quantities out. We want to relate them and see what's going to be required to cause this relationship to hold. So dn dt in our control mass is the stuff in our control mass at time t equals delta dt minus the stuff in our control mass at time t equals 0 divided by the time increment. So that becomes d plus f plus g at time dt minus b plus e plus b plus f plus c at time 0, all divided by dt. Okay? And then we'll do the same thing for our control volume formulation here. At time dt we have a plus b plus d. A plus b plus d minus this same quantity here, b plus e plus d plus f plus 0, or plus c, all again divided by dt. And we need to add something to cause this relationship to hold. So we'll notice right away that we can just separate these in terms of two fractions, and these two terms here are going to cancel. So we're left with d plus f plus g at some time dt minus a plus b over dt. It's going to equal whatever we need to cause the relationship to balance, is that time dt. So let's see, d's are going to cancel, and we're left with f plus g over dt minus a plus b over dt. Now, what do these terms actually mean? So we just did accounting, not just in terms of areas. What do these terms actually mean? F and G. F and G are things that are, those are the outflows from our control volume. Those are things that our control volume contained that now the control volume no longer has in it. So this is nothing more than our out minus, and then A plus B are things that the control volume has in it now, which the control mass does not have anymore. So these will be inflows into our control volume. Minus in. And so we're left with the control mass formulation, which we can use to we can use our physical principles: mass is conserved, energy is conserved, Newton's second law for momentum, etc. It's related to the stuff inside of our control volume, the accumulation of stuff, plus the outflows minus inflows. So let's do this more we could continue this derivation rigorously to get to the mathematical formulation, but I think that this serves the purpose of what we're trying to do here. So let's talk more about the mathematical formulation. So if our quantity we're conserving is n, we're going to conserve the specific quantity at eta, which is n over m. These are the intensive property eta. And so we know that dn dt in our control mass is the rate of change of eta in our control volume plus the flux terms, integral over the control surface of rho eta times the dot product of stuff leaving the control surface with the surface normal times the area. Okay, so let's talk about what each of these terms mean a little bit further. So again, we can exploit the laws of physics here to talk about, this is like the mass conservation, energy conservation. You can think of rho dV, integrated over the volume is just a mass. We're multiplying mass times our intensive property gives us n, so dn dt. And then here we're talking about balancing the quantity eta, where eta multiplied times the mass flow rate out of our system minus inflow to our system. And the reason it's out minus in just because the unit vector n hat is defined positive outward from our control volume. Okay, so now we're going to be doing momentum balance, and we're going to apply this principle to n equals mass times velocity. And we're going to write out Reynolds Transport theorem applied to linear momentum. So we have d mv dt, which we know from Newton's second law becomes m dv dt, or ma, or just sum of the forces. So this is the sum of the forces. And the reason we can relate, this is actually the sum of the forces on our control volume. And the rationale behind this is that at time t equals 0, our control mass and control volume were coincident. Which means that the sum of the forces on our control mass is the same as the sum of the forces on our control volume. So this is the left side. Now we're going to be balancing velocity, linear velocity. And we need to be careful about which reference frame we're balancing our velocity in. So whenever we deal with this, we need to know what eta is. And for velocity, that means we need to know the reference frame in which we're measuring the velocity. So just keep that in mind. Plus the flux terms. And these velocities are currently notated to be the same, and they could be the same, but it's not always the case that they're the same. So this is where it's really important to understand Reynolds Transport theorem rigorously. This quantity here is the stuff we're balancing. If we're balancing velocity in an inertial reference frame, causing velocity in a non-inertial reference frame, Newton's second law does not hold. We need to subtract out the mass times acceleration of the reference frame. This velocity here is always going to be relative to the control surface. Because all that this is saying is the stuff that's crossing the control surface relative to the control surface. So this is always relative to the control surface. This velocity is relative to our reference frame, which is not always the same thing as our control volume. If our control volume is accelerating and the reference frame is fixed, this velocity needs to be relative to that fixed reference frame, whereas this velocity needs to be relative to the control volume. Okay, so now in this lab we're going to be applying linear momentum balance to the x direction. So we'll just do a single direction of balance. So we can apply this whole equation just to some of the forces in the x direction. And our quantity we're balancing is now Vx. Which means this velocity now becomes Vx. But it does not mean that this velocity is Vx. So remember, this velocity is always the true vector in 3 coordinates, 3 dimensions, outward to the surface normal, times dA. Okay, good on momentum balance? Awesome. We're going to go look at the experimental setup now, and we're going to do more board work to derive the equations to govern the experimental setup, and then we're going to do some Matlab to correlate the experiment results and the analytical results. Alright, so this is the water cannon. It is a rigid object held up by 2 flexible plates, which provides motion in the x direction only. And what we're going to do is we're going to spit water out of the nozzle at this end, and we're going to counteract the momentum flux, which would cause an acceleration, via a reaction force on the back, which we'll measure using a force gauge here. So let's look at the system and identify all the components that we can and explain them. So what do you see in this whole setup? We could talk about every component on its own. So working left to right here, let's see, we've got this green box here. This is a solenoid. It is a valve, so when the valve is closed, the system will be sealed off and we can pressurize air inside of it. When we open it up, the pressurized air will drive water out of the nozzle, and we can close and open the valve, the solenoid valve. If you come down here to the switch box, closed, open. We see, let's see, well, there's a tank here for water. It's measured in liters. We're going to be filling this tank up to 2 liters of water. And if you look inside the tube, it's kind of hard to see, but there's a tube that dips down into the bottom of the tank here. That's a dip tube, and it runs the length of the device up and around to the nozzle, which is attached to the valve. And so the water is going to get ejected out of the nozzle via some force that's pushing on the free surface of the water, and that will be the pressurized air. So the top part of this tank will be filled with pressurized air, which we're going to pressurize using this tube here, which if you follow up, you see there's a force gauge. It's a Bourdon gauge registering in PSI, and we see it's at 0 right now, which means this is measuring gauge pressure. And then behind it you'll see an electronic pressure transducer, a little metal can. So that's measuring the same pressure that the visual gauge is reading. And that is hooked up to the computer with a USB port, and we're going to register, we're going to keep track of all of that pressure data on this computer interface. This plot down here is going to be the pressure data that we're going to get. And of course it's outputting in volts, so we're going to be plotting in volts, and then we're going to relate those volts to pascals later in Matlab. The other plot up here is the load cell. This is the force, the reaction force that we're going to be applying to counteract the momentum transfer. And again in volts, and we're going to see these plots evolve over time, and we're going to save this data in a text file. So right now I've opened up what I've done to get here. I'll close out to show you. We have a folder, Water Cannon LabVIEW VI. Any of these files will work. I'm working on Spring 2013 right now. and I want to save my data so I can plot it later. So I'll navigate to a window where I want to save my data, and I need to actually create a text file first. So new text document, I'll call it test1, and then we need to select it and open it. And now that data will be saved to the text file, which we labeled test. Okay, so back to the setup here. We said this was a line for pressurizing the air. If you follow the hose back, it goes back to this air compressor here. The air compressor has a dial on it that it's a regulator. We can specify the maximum pressure that's going to compress to. Right now it's at 50 psi about. Working our way further, we have the spot for water to come in. So what we're going to do is we're going to take our hose, which is hooked up to the sink. There's a sheath on the hose. We're going to plop the hose onto the pipe there, open up the valve and turn the water on. The reason I'm not touching it right now is because I am afraid that if I jostle the device, I will hit the force gauge and I can easily break the force gauge. So that brings us to the last component of this device. This is a strain gauge, okay? We have one right here, which is broken, that we've taken apart. And the way a strain gauge works is we're exploiting the property of electrical resistance, which is a function of the cross-sectional area and density, cross-sectional area and length of a wire. So we're going to be changing the resistivity of wire via elongating the wires. And how we're going to elongate the wires is we're just going to, as you can see, very small, you might not be able to see it in the video, but fine mesh of wires running back and forth. So there's a lot of wires in series, and so a small cross-sectional area change of every wire summed up over all of them will create a noticeable change in resistance. And so we're going to change that cross-sectional area by pushing on this flexure element here. And if we know the change in resistivity and we know the geometry of this flexure, we can back out what the strain in this material is. And if we know the strain, we know the Young's modulus, we can get the stress. And if we know the area over which we're pushing, we know the force. So it's a pretty cool device. They're used all over the place. They are also pretty sensitive, so we're getting, this guy is maxed out at 10-pound force. So we can break it if we apply a force greater than 10-pound force. And that's not hard to do. So if we push it to hold it away from the strain gauge, I'll feel more comfortable filling the whole thing up with water. But we have to be very careful not to let go because we will plastically deform the flexible element and then break the strain gauge. Okay, so now we're going to fill up the water cannon. We have Matt here helping to hold the device away from the strain gauge. So I'll put the hose on the thing there. The valve is currently closed. I'll open the valve. The green valve has to be directed parallel to the direction of flow. So we'll fill it up to 2 liters. We're right on the money. And we'll notice right away that the pressure on the pressure gauge went up. It's about 8 psi right now. That's because we just displaced or compressed some of the air inside because we have a closed system. So next step is we need to pressurize the air the rest of the way. We're going to pressurize up to about 40 psi. So we've got to open up this hose here and then turn the compressor on. Now this is very important. Oh, right. I also need to take off the water hose so that we don't restrict the motion in the extraction. Thank you, Matt. Close that. Take the hose away. Now I can pressurize the air. So if I turn the compressor on and then close the valve after we've got the 40 psi, I'll be compressing the air in the hose, which is dangerous for the hose. So we'll turn the compressor on, wait for it to get above 40 psi, turn the compressor off, and then close the hose for the air hose. Now you want to turn the compressor on? close cap valve. So now she's live, ready to fire. Matt's going to gently pull the thing back on the strain gauge. We make sure this is sort of looped up here so there's not too much resistance on it. We're all clear. This elbow joint is crucial for the experiment. We'll have a volunteer hold with 2 hands. Be careful not to touch the nozzle, directing the flow into the water. And we'll have a volunteer on the computer clicking the small white button up there. Okay, so Matt's going to click the run button on the lobby interface. I'm going to hold the elbow joint. He's going to come around and flip the switch.
Cool. 3, 2, 1.
Perfect. So, close the solenoid, and let's go look at the data. So, what do we see? On the top plot, we're getting our force data from our load cell. The flip was switched at about the switch was flipped at about 2 seconds in, and we see some serious transients in there. And then the experiment lasted until about, let's say, 6.5 seconds, and we see something happen. This is the pressure down here on the bottom. So the first, we'll notice that the transients occurs when the switch gets flipped. And the reason for that is just because we are impacting the load cell, and there's going to be some bouncing back and forth of the whole device. So we're visualizing the damping and the damping characteristics of the whole setup. So the oscillations of damping are getting damped out until we reach some sort of a constant force applied to the load cell, or a steady, at least steadily declining force. And the same thing occurs at 6.5 seconds. We'll notice on the pressure plot it's smooth just because pressure is not as dynamically measured. And then at 6.5 seconds, what happened there is the water ran out, and we're starting to see an air cannon instead of a water cannon. And the load was released from the device at this point because the water is the force the water exerts is, or the force due to the momentum flux of the water is less than that for air because of the density of water. And we see it getting released, and then the same damping characteristics happen, getting it back to equilibrium. So this data will be saved in a text file. We'll have a column of time increments from 0 to 10. We'll have a column of voltages coming from the load cell, a column of voltages coming from the pressure transducer, and we're going to want to save this data in a text file. We're going to import it into Matlab. We're going to derive the equations that are going to govern this theoretically. We're going to plot the two overlaid on top of each other and see how we do. Okay, so we're going to try to run through the derivation of those equations. So to begin with, let's write the system on the board. We've got this tank. We've got a dip tube which runs down to the bottom of the tank with some water. We've got a jet that has velocity Vj, which is a function of time, and we'll say there's some area of the jet. We know that the diameter of this nozzle, this pipe here, is 1/4 inch. And we know there's some force acting on this side of the device. So the first step in any problem, we'll define our system. So let's draw our control volume. I'm going to make my control volume just around the water itself to make things simpler. You could draw it around the entire device if you wanted to. It would just, the air term would drop out anyway, but this is more intuitive for me. Label this as our control volume. And let's think about what our unknowns are here. So we want to plot P, and I'm going to say it's P air as a function of time. And that'll be the pressure inside this chamber. We want to plot force as a function of time. And we know, just first off, right off the bat, that force will probably be a function of this velocity, because we know from momentum balance that there's going to be that term, the flux term in there. So that's going to be another unknown. Vj is a function of t. And as we go, we'll see there's going to be another unknown, which is going to be the volume of the water, or the volume of the air, but we're going to, since we know the initial volume of water, we're going to keep that as our unknown. So I'll say Vw is a function of t. Okay? So, first things first, we have 4 unknowns. We'll need 4 equations. which equation should we start with? I tend to start always with mass balance. Mass balance will always be useful, or not always useful, but it's always true, and it oftentimes is more useful than you think than it might seem, because you'll use mass balance later on in momentum balance. So we'll do conservation of mass. So Reynolds Transport theorem applied to mass. 0 is the okay, so our term inside here, rho for our water is going to be uniform in the volume, so that comes out. And we're left with the integral dv, which is just v. So rho will also be constant in time, so this becomes rho times dv water dt. And our flux term, we only have one flux term, it's going to be an outflow, and the normal vector is happening in the same direction as the outflow. So it'll be a plus rho vj aj. Solving for dv w dt is negative vj aj. And we could have intuited this just by virtue of the fact that the volume is changing, and we know it's an outflow, so the volumetric flow rate out is equal to the change in volume in the tank. Okay, that's one equation. Let's write the equations over here. Next equation we might think to use is maybe momentum balance, since we know we're going to have to solve for that force over there. And before I can start with momentum balance, I just want to explain one thing about this force, in that right now I don't have it touching my control volume. However, this is a rigid container, so we're not going to be caring about moment balances. So I can apply this force anywhere along the side, and I will just move it over here for simplicity. This is just because I chose my control volume to be just the water. And momentum balance gives the sum of the forces, and if we draw our coordinate system this way, sum of the forces is just one force. We only have one surface force, and it's the negative F direction. We could do a pressure force over here, but it's just a free jet expanding out to atmospheric pressure. So it's counteracted by all the atmospheric pressure on the opposite side of the control volume, so there's no pressure forces. And the only body force we deal with typically is gravity, and the gravity is acting in the y direction, so we are okay with just negative F. And then our accumulation term, we're balancing x velocity here, and our flux term, again, x velocity is being balanced. So the accumulation term here, remember this is an integral over the control volume, so we're summing up volume elements inside of our water, and we're multiplying times the x velocity of those volume elements. So this turns out to be small. The amount of mass, this becomes dVt of m Vx. The amount of mass that has x velocity is only the stuff that's entering this tube right here, and the stuff sort of in this region of the tube. And to make our lives a little bit simpler, we're going to say that's a small amount of mass. So this whole accumulation term is going to be small. Now the flux term, we'll do this real quick. We have our rho. Our Vx right now is in our negative Vj term, so I'll put a negative out in front. And then our V dot n is again positive Vj, so that's a Vj squared, and our Aj is there. So we're left with the thrust force is equal to rho Vj squared Aj. Sorry, this is a reaction force to counteract the thrust. Is rho Vj squared Aj. So that's equation number 2. So we know we're going to need another expression for Vj in order to evaluate force. So what can we use for the Vj term? Well, we'll use Bernoulli's equation, which relates the energy along a streamline. So we'll start at state 1, which is the free surface of the water. We can draw a streamline that goes all the way up through the dip tube out to point 2, which is our atmospheric point. So Bernoulli's we know is P1 over rho plus GZ1 plus V1 squared over 2 equals P2 rho plus GZ2 plus V2 squared over 2. So first recall the Bernoulli's equation only holds for inviscid flows, and we typically only think about it for along a streamline. The streamline assumption could hold fairly well. We could think of a fluid element going along this path. The inviscid assumption turns out to be not great. Turns out that in the nozzle here, we have a huge amount of turbulence where we have a contraction. The nozzle just is simply a chamber which is restricted down into a lower area. So this region in here requires some sharp bends and some turbulent eddies that form. And we can't neglect that, the inviscid nature of this flow here. So we're going to try to account for this in a second. Just keep that in mind. So let's drop terms here. First, what's V1? V1 is the velocity at this point here. And we're going to say that's small relative to V2 because this is only dropping slightly in the y direction, but just only slowly. So V1 will go to 0. Now, P1 is our P-air, but P-air we know is measured in gauge pressure, so the absolute pressure will be P-air plus P-ATM. But P2 is P-ATM, so we can say P1 minus P2 is just P-air. And now GZ1 and GZ2, we could include these terms because we know the height difference, it was about 1/2 meter. But if you look at the magnitude of the velocity versus the magnitude of the potential energy difference, let's see, Z2 minus Z1 is maybe about 0.5 meters, G is 10, that's 5 joules per kilogram. And V2, let's say about 10 meters per second. Square that is 100, divided by 2 is 50. So these are an order of magnitude less than the velocity term. So I'm going to neglect those guys. So I'm left with P-air over rho is equal to V2 squared over 2. Now here's where we need to, well, not quite yet. So we'll solve for V2 really fast. V2 is just square root of 2P air over rho. But this velocity here assumes inviscid flow, no losses in our nozzle. Turns out this nozzle business is not negligible. We need to account for it. So we'll use what's called the discharge coefficient, C sub D, which is defined for, start over here again better. It's defined for any sort of contraction or expansion, let's see, as the ratio of volumetric flow rate in the actual real world, or what it would be if it were inviscid, so in this region here. So for a perfect nozzle, you have no losses and you get the ideal volumetric flow rate. Of course, we have some losses, so it's going to go down. We know that the area in both cases are the same, so this just becomes V actual over V ideal. And if we look at our Bernoulli's equation, we just use V2, which is our ideal velocity, since we assume it's inviscid. So we're going to try to plug in for ideal velocity there. So V ideal equals V2 equals V actual over C sub D. Now C sub D is an empirically measured quantity. For nozzles of this type, for this sharp contraction, it's about equal to 0.6. For better, more gentle constrictions, it's more like 0.9. And we actually could do an experiment in the lab in which you would measure CD. But we'll use 0.6 for this experiment. So we know that V2 is up here, and V actual is the actual velocity of what's coming out of the nozzle, which in our case is Vj. So this is Vj over Cd. So we're left with Vj, as a function of time, is C sub D times the square root of 2p air over rho. That's our third equation. So we definitely need one more equation still. And this last equation is always the one that people tend to forget. So right now we have our only unknown we haven't had accounted for is P air. So we need to use our E30 knowledge to come up with an expression for how P air relates to the other variables. So whenever we have a process here that's involves air expanding, we need to think of a variable which is going to remain constant during this process. So definitely not pressure. No reason for temperature to remain constant because there's no heat flux. I'm not allowing for any heat flux. We're not providing any heat flux to counteract that expansion, the temperature drop due to the expansion. You might think that it would be isentropic. So it could be an ideal expansion in which there's no heat flux, it's adiabatic, and it's reversible. The reversible assumption is valid because we could think of it as being a compression with water being pumped into the tube and compressing the air. We're not compressing to very high pressures, so there are not a lot of losses. And the adiabatic assumption is valid because the walls are relatively thick plastic, and the process happens quickly enough that the thermal time constant or the heat to go into the system is long compared to the experiment time. So it's adiabatic and reversible, therefore isentropic. So S is constant. And we know that for isentropic processes, we can write the expression P V to the gamma is a constant. Of course, this is the absolute pressure, so you guys be careful about that. And we know at time t equals 0, we know both the pressure, because we read it off the gauge, and the volume, because we filled it up to 2 liters. So we can say P air naught, which we know is measured in gauge pressure, plus P ATM times the volume of air, and we want to deal with volume of water here, so it's going to be V total minus V water at time t equals 0, raised to the gamma is equal to P air at any time t plus P ATM times V total minus V water anytime t raised to the gamma. So really quickly, we'll write out the expression here. P air is equal to P air naught plus P ATM times this big ratio raised to the gamma, and we need to subtract P ATM. Okay? This is our fourth equation. I'm not going to write it on the side, but this is what the fourth equation is. Actually, I will write it on the side. So we Okay, so now how are we going to solve these 4 equations? Well, we know that force is not coupled to the other equations, it's just a function of Vj. So we can think of it as 3 coupled equations. One of which is an ordinary differential equation. What I would do is I would plug them all into, substitute them all together and have one long expression, one long ODE, and then we can try to solve that ODE. So let's do that. Let's just plug in, we know P air, plug that in there, Vj, plug that in there, and we'll get one expression all in terms of one dependent variable, which is Vw. So, bear with me here, don't get lost, because this becomes just cumbersome mathematically, but the theory behind all this is completely within our realm of knowledge. We know how to get from a picture down to the equations for force and pressure, which we want to plot. So I've got negative Vj, Vj is our long expression, negative Aj CD times the square root of 2 over rho times P air naught plus PATM times this big fraction raised to the gamma minus PATM. And that is our single ODE. Our only unknown is VW, the rest are constants. And how are we going to solve this? So it's clearly not easily separable. In fact, I'm not sure if there is an analytical solution to it. So let's talk about how to do it numerically. So what we're going to do is we're going to express our derivative here in terms of a finite difference. We're going to try to model or try to approximate this derivative by just delta VW over delta T. So the definition of the derivative we know is the limit as dt goes to 0 of VW at t plus dt minus VW at t over dt. And if we try to approximate this with a finite time increment, we can call this dt a finite value delta t. This approximately equals VW at t plus delta t minus the first value of t over delta t. Okay, so now working our way from time t equals 0 to some other time at t, we can use the linear approximation to the derivative to jump forward in time. Because we have that slope of this curve, because we know dv, w, dt. So I can discretize our time domain into small increments. And at any time, let's say this is index I, time index I, we can express the I plus 1th value using the last one I. This is called forward differencing. So I can express VW at I plus 1, which is this value here, is equal to the old value, VW at t, or VW at I, VW at, well, yeah, right, plus the slope of the curve, dVW dt, times our time increment delta t. And this slope here needs to be evaluated at a point in which we know, which we'll say is the ith index point. So this is our forward finite difference method. There are other finite difference schemes that are higher order, so we could approximate this with a polynomial instead of just a straight line. There are backward finite difference schemes in which you take a point behind, or you use a point in front of you to calculate the point behind you. Central finite difference schemes in which you use both ends. And there's a whole algebra of this stuff. So we're going to apply this to our equation here. And we're going to want to do this in a for loop in Matlab because we're going to want to increment our time from time t equals 0 to some time t at the end. So let's write out a skeleton code of what our code is going to look like. And so I'll give you some of the basics, and then you're going to want to fill in the blanks and try to add a few more things to make it run. So I'll do it over here. The first thing we want to do is define constants. The script that you should have, you're going to have a stub file. It's going to have some of the constants defined, such as AJ, CD, the atmospheric pressure, rho, etc., V total. Recall that V water at time t equals 0 was 2 liters. And there's also going to be a part of your script in which you are going to be able to calculate the first time value, or first pressure value, using the experimental data. So that's going to be taken as a known, and we're going to read it in from our data file. So that will be treated as a known as well. So we're going to define constants. Then we have to create our whole time domain here. But before we do that, we need to decide what our time increment is going to be. I'm going to say our time increment dt is 0.001, arbitrary. And I'll create our time vector here, t, which will be a vector from 0 at increments of dt all the way to t end. And t end is actually a known quantity which is going to come from our experimental data. It's just the time this whole experiment to happen. It's t underscore n in the Matlab script currently, but you should double check what that's going to be. Then we want to run our for loop to start calculating our VW vector. And once we have VW defined, we can define everything else because it just drops out from Pierre, which gives us VJ, which gives us force. So the Matlab syntax for a for loop goes as follows. For an index I equal to some value at increments of 1 to some other value. I'll let you guys decide what these bounds are going to be. We need to populate the next value in time of VW, and it is equal to everything up there, which I will write down laboriously, minus AJ CD square root of 2 over rho Pierre naught plus PATN. Remember, this is evaluated at the ith index, so we're going to use the old value of VW in this derivative expression. All raised to the power gamma minus PATM, close parentheses, close square root, and don't forget to multiply times our time increment delta t. Alright? And then we will close our for loop. And once we have VW, we can solve, like I said, for Pierre, VJ, and for force, and then we want to plot. So if you write the script up as it is and try to run it, you're going to come up with problems. The errors you're going to have to debug on your own, but some of them will definitely involve the bounds on your for loop. And you're also going to run into problems with the first value of VW at I. We currently have no VW defined, so we'll have to think about that. Okay, that's on you. So let's go now to the result of the Matlab, and then we'll talk more in a second. Alright, so now we're on our Matlab. We've downloaded the scripts that have already been posted on coursework. And we have a water cannon stub file, which just consists of the importing of the data. And I've already put all of my files in the right directory with the text file, which we pulled off from the other computer. And I will rename the file name to the current text file name. And if I just try running this guy, you'll see there is a plot which is identical to the pressure plot we saw on the other screen, and it tells us to click the coordinate at the starting point of the experiment. What we're doing here is we're just trying to specify the time of our experiment. We're only modeling the point where the water is expelling from the water cannon. So I'll denote this as my first point, and the second point is at the end of the water. Great. So now I have stored in memory. If you look at the Matlab script, the output of this function load x data is time, p experimental, and f experimental. And I want to keep those in memory, so I'm just going to comment this out, making sure that the clear all command is not happening, which keeps the data in memory. So now what I'll do is I would continue to write my Matlab according to what's on the whiteboard, but to save time here, I'm going to go to the end. So this is a script which already exists, and will perform the same process here. And we'll see that we're plotting volume of water, jet velocity, thrust force, and air pressure. Now the air pressure looks great. The blue line is what we measured in the experimental setup, and then the red and black lines are both models, the analytical model. They all agree fantastically, which is pretty cool. The difference between the red and the black model is using the black line is the experimental or analytical model using MATLAB's ODE45 function, which uses a higher order finite difference scheme, which will be better at approximating the derivative, but they're pretty much identical. So that will be a good thing to have if we have extra time in the lab. If you want to work on getting ODE 45 set up instead of doing the forward difference scheme yourself, that would be a good practice, a good thing to do. This plot here is the thrust force, and we see it's more oscillatory, and this data is actually already filtered as it is, but it would be coming out of the computer even more wacky, and it also agrees fairly well. Looks like we're off by about 0.5 newtons. That's probably because the zero on the force gauge is not exactly the same every single experiment, because it's been deflected a little bit, just plastically yielded by other groups. So we see our plots agree pretty nicely. What we've done so far in this lab is we have ran through momentum balance. We looked at the experimental setup and discussed the different components of it. We ran it, gathered experimental data on the pressure of air inside the water cannon and the thrust force that's exerted on the strain gauge. And then we did an analytical model of the whole setup, and then we compared the two, and we see pretty good results from our analytical model. So that's the water cannon lab.